This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some relevant concepts associated with the released FreeResponse question BC2 from the 2021 AP Calculus exam. My name is Steve Kokoska. I'm a professor emeritus at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. The FreeResponse portion of the BC AP Calculus exam almost always contains a problem that involves particle motion in the plane. And although students and teachers have become very accustomed to these types of questions, there are still several concepts that I would like to emphasize in this video. It seems to me that most of these FreeResponse questions contain problems that ask about these 5 concepts: velocity and speed of the particle, the distance traveled by the particle, acceleration of the particle, and finally the position of the particle at a specific time. Certainly there are other comprehensive questions asked involving particle motion in the plane, often involving the chain rule, but these 5 topics have become pretty standard. And I think if a student masters these topics, they'll do very well on this type of particle motion question. So, I intend to quickly review these ideas and then solve a few examples. And since these questions often appear on the calculator active portion of the exam, I'll be using technology to solve these problems, explore solutions, and to visualize results. Let's start with a basic review of the important concepts associated with particle motion in a plane. Suppose a particle moves in the plane so that its position at time t is given by the parametric equations x equal f of t and y equal g of t. Note that in these AP Calculus exam questions, the description of particle motion can be given in many forms: analytically, that is, with equations for f and g, with a table, or even a graph, and sometimes we're given expressions for the velocity of the particle. In particular, we are often given a vector function that describes the motion of a particle in a plane. The functions f and g are called the component functions of r. R of t is the position vector of the point P in the plane. So any continuous vector function r describes the motion of a particle in 2 dimensions, and also defines a curve C that is traced out by the tip of the moving vector r. In this context, the velocity vector v of t is given by this expression. It's the derivative of the vector function r, and it's found simply by taking the derivative component-wise. The speed of the particle at time t is the magnitude or the norm of the velocity vector, written using this notation and computed using this formula. Just a few other important concepts, and then we'll solve a few problems. The total distance traveled by the particle from time t equal alpha to time t equal beta is given by this definite integral expression. And the acceleration of the particle at time t is defined to be the derivative of the velocity. In vector format, it's written in this manner. And finally, we often need to use the fundamental theorem of calculus to find a new position of the particle. So, to find both the x and the y coordinates, we use the FTC, or the net change theorem, twice. For example, the x-coordinate of the position of the particle at time t equal t sub 1 is the initial position of the particle at time t equal t sub 0 plus the net change in position. Okay, let's try to put these concepts into practice. I think this is a very typical AP Calculus type question. Suppose a particle moves along a curve in the plane such that its position at time t is given by these expressions. First, let's sketch the path of the particle. We'll probably need technology here. Then, find the velocity vector and the acceleration vector at time t equal 1. In part C, let's find the speed of the particle at time t equal 3. And finally, let's find the time at which the particle is farthest to the left. And let's find the position of the particle at this time. I'm going to use technology to sketch the path of the particle. Now, if we were to do this by hand, we could start by creating a table of values, and then plot some points and connect the points with a smooth curve. It's a little tedious, but we could do it if we had to. Technology makes this much easier and quicker, and it presents a much more accurate visualization of the curve or the path of the particle. Using the TI-Nspire CAS calculator, the first thing I did was to define the functions x and y. Then I changed the graph type to parametric and entered the expressions for the x component and the y component. Notice that I also changed the interval for t and the t-step value. Generally, the smaller the t-step, the more smooth the curve. However, sometimes it takes a little longer to produce the curve. Here's the path of the particle, and it looks a little like part of a parabola. Now, we often want to determine the direction of the particle along the path. And one way to do this using technology is to trace the curve. On the bottom right side of this screen, I can see the value of t and the corresponding x and y coordinates. As I increase the value of t, I can see the motion of the particle on the curve, and therefore the direction of the particle as t increases. To find the velocity vector, I simply take the derivative of the position vector piecewise or component-wise. And then I evaluate each component at t equal 1. So the velocity vector at time t equal 1 is e minus 7, 3. Geometrically, the velocity vector is also the tangent vector, and it points in the direction of the tangent line to the curve. To illustrate this idea, I have a graph of the curve, and I found the position of the particle at time t equal 1, and I sketched the velocity vector at that point. I still need to find the acceleration vector, so I take one more derivative of each component, evaluate each at t equal 1, and so the acceleration vector is e minus 2, 2. To illustrate this concept, I've graphed the curve again, and this time with both the velocity vector and the acceleration vector at t equal 1. I think there's some interesting ideas to think about here. I mean, it looks like in this example that the velocity vector and the acceleration vector are perpendicular. Now, I don't want to mislead you. That could be, but in general, these two vectors are not perpendicular. Now, it certainly looks like the velocity vector is pointing in the direction of movement of the particle. I wonder if you can find a similar geometric interpretation for the acceleration vector. I want to show you how to solve this problem using technology. It's pretty cool. On the TI-Nspire, I can actually define the two derivative functions. And here, I called them xp and yp. Then, using calculator vector notation, I found the velocity vector at time t equal 1. Well, I can also define the components of the acceleration vector by using the second derivative function. And here, these functions are called xpp and ypp. Okay, for x double prime and y double prime. And finally, I found the acceleration vector. Note that these component values are given symbolically. I'm working with a CAS machine. That's pretty neat. To find the speed of the particle at time t equal 3, I used the formula for speed, the velocity vector, components, and technology. I found the speed to be approximately 11.469. Now, I didn't introduce any units into this problem, but remember, often units are explicitly asked for on the AP Calculus exam. And here's how I found this answer using technology. Remember, I already have xp and yp, those functions, defined. I first found the answer symbolically, and that's the exact analytic answer. And the numerical approximation is also here. Part D is a good question. I like this one. And we often see questions like this on the AP exam. When is the particle farthest to the left? To solve this problem, we need to consider the horizontal position component function x. And we need to find the minimum value of this function. So I need to find those values of t for which the particle changes direction in the horizontal direction. And that would be the times at which the horizontal velocity is 0, or doesn't exist. So I need to search for critical points. Consider the expression for x prime of t. It's defined for all values of t greater than or equal to 0. So I set the expression equal to 0 and solve for t. Now I have to solve this equation using technology. And I found only one value, t equal to 2.252. My sign analysis showed that x prime of t is less than 0 for all values of t less than 2.252, and greater than 0 for all values of t greater than 2.252. Therefore, the horizontal component function x has a minimum value when t is equal to 2.252. And here's the position of the particle at that time. Here's how I use technology to find this value of t and to graphically confirm my results. I like to use the calculator function zeros to solve this equation, x prime of t equals 0 for t greater than or equal to 0. I use this function because the calculator places the values, the results, in a list. And then I can reference each element of the list using subscript notation. This is important since I can pretty easily refer to and use the value or values found to the greatest degree of accuracy allowed by the machine. So here's the value of t. And here's the position of the particle at that time. And here's the graph to help confirm my results. The path of the particle is in blue, and the point corresponding to t equal 2.252 is plotted on this graph. It certainly looks like it is the farthest point to the left. I feel pretty confident about my answer. Here's one more example involving particle motion in the plane. And this time, we're given the velocity components. We need to find the speed of the particle at time t equal 1, the distance traveled during this time period, and the average speed of the particle over that same time period. I used the formula for speed, and I really need some help with technology on this one. I defined the function xp for x prime and yp for y prime. And then I simply used the appropriate formula to find the speed of the particle at time t equal 1. And my answer is 2.483. And here's another nice feature of the TI-Nspire. Just in case I need to use this value for speed in another calculation, I stored the value to a high degree of accuracy in a variable that I called speed. To find the distance traveled by the particle over the interval 1 to 4, I used the appropriate integral expression. Boy, there's little hope of me finding a symbolic antiderivative here. So once again, I used technology to find the total distance traveled is 70.943. Sorry, no units in this problem either. But one important technology tip. These expressions for x prime and y prime are fairly complicated. It's a good idea for students to enter these once into their calculator, to define functions for x prime and y prime, whether it's like what I did on the TI-Nspire, or using the variables y1 and y2 on the TI-84. Then use these function names in subsequent calculations. This decreases the chance of making a typing error. And the same advice goes for writing solutions on the exam paper. Use the named expression for a function wherever possible, especially if it's complicated. This decreases the chance of making a copy error and makes it much easier to ensure parentheses and brackets are balanced and the correct expression is raised to the correct power. And just in case I need to use this distance traveled in another calculation, I stored the value in a variable called distance. And in part C, we need to find the average speed of the particle over the time interval 1 to 4. Well, average speed is total distance traveled divided by the elapsed time. So I used the value from part B, and the elapsed time is 4 minus 1, or 3. I'll use technology to find this value. I used the value stored in the variable distance divided by 3 units of time. And the average speed over this time interval is 23.648. I hope this video provides a nice summary of the most important concepts associated with particle motion in the plane, a few AP Calculus type questions, and some examples of the use of technology to solve and visualize these types of questions. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.